Hi, welcome back to Statistics 1. We're up to Lecture 8, and the topic of Lecture 8 is null hypothesis significance testing, which is a fundamental topic in statistics and a somewhat controversial topic. So we'll talk about the basic logic of null hypothesis significance testing in the first segment of this lecture, and then in the second segment, I'll talk about why it's controversial, why there are some problems with it, and then we'll talk about some of the remedies that you can apply to deal with some of those problems. So this lecture will just have two segments. As I said, the first segment I'll just give an overview, introduce the process of NHST, and then in the second segment we'll talk about why it's such a controversy, and we'll talk about the problems and then how you can address those problems. So first, an overview. Null hypothesis significance testing, when I teach undergrad statistics, I refer to it as a game. It's a game we play as scientists who do research. Not all of us play this game. There are many scientists out there, especially in the last decade or so, who have argued very vehemently that we should stop playing this game and that we should ban null hypothesis significance testing from all of scientific research because they argue it's very misleading. I don't take that position. I don't describe myself as pro-NHST, but I'm also not anti-NHST. I think if it's taught appropriately, which hopefully we can do in this lecture, and you understand what it can do and what it can't do, then you'll be fine. So let's talk about how it works. And again, it's nice to think of it as a game. This is a game we're playing as we're conducting our research. So before we conduct a study or an experiment, we set up two hypotheses. One I'll call the null hypothesis, and that's just H sub 0. So if we're doing, say, a correlational analysis, the null hypothesis would just be R equals 0. The alternative hypothesis would be, say, I'm expecting or predicting a positive correlation. So R is going to be greater than 0. That's the alternative. So this is how the game starts. Step 1, identify the null hypothesis and the alternative hypothesis. We could do this in regression as well. So here, the null hypothesis is that the regression coefficient, the slope between x and y, is 0, and the alternative is that it's positive. Our hypothesis is we're predicting a positive relationship. If the alternative hypothesis it predicts the direction of the relationship in a correlation or regression analysis, as I just showed you there, then those are known as directional tests. We could be more agnostic about what might happen in a study or an experiment and not predict the direction, so that's known as a non-directional test. You might have heard of these before. The directional test is sometimes referred to as a one-tailed test, and the non-directional a two-tailed test. And we'll talk about why that is in the next lecture. So again, here would be the setup for a non-directional test in regression. So the null is still that the regression coefficient is 0, but now the alternative is that it's just not equal to 0. It could be positive, it could be negative. And that exclamation point equals, remember, that's how we, that's the notation for not equal to in R. So I'm going to use that. I'm going to start to sneak R notation into the lectures now that you're getting familiar with R. So step 1 of the game is we just state the null hypothesis, state the alternative hypothesis. Then going into our study, this is the weird part, one of the weird parts. We have to assume that the null is true. Then do our study, calculate all our statistics, and then reassess that assumption. That's sort of odd and backwards, and this is why critics of null hypothesis significance testing say it's just a weird approach to science, because very rarely are we predicting Nothing, right? Very rarely do we develop theories that predict no relationship between two variables. Jonas Salk didn't predict that his vaccine wouldn't work. So it's rare that we're looking for no relationship. So it's a little bit weird and backwards. But anyway, that's how it's going to work. We're going to assume the null is true, do our study, calculate some statistics, and then we can estimate the probability of observing the data that we did observe given that initial assumption that the null is true. That gives us a p-value at the end. And if you've had any exposure to research or just reading about research studies online or in the news, you'll often hear this phrase, the relationship was statistically significant, p less than 0.05. This is where that comes from. So if we get a very low p-value, for example, less than 0.05, so if the probability of obtaining the data we obtained, given the assumption that nothing was going to happen, if that probability is so low, like less than 5% chance, then we reject the null and we say, hey, it looks like the null hypothesis was wrong. Looks like there is an effect here. There is a relationship between x and y, for example. So that's how the game works. And if you play this game, you have to be prepared for one of these four outcomes. So strictly speaking, if you're doing an NHST, you're going to wind up in one of these four boxes. So the way I demonstrate this in my undergrad classes at Princeton is think of these two rows in this table, which I've labeled truth. Sort of like the truth is out there. We don't know what the truth is, right? That's why we're doing the research. We don't know if the null is true or if the null is false. We don't know. So that's why we're doing this. So the truth is out there. So think of these two rows as alternate universes. They can't coexist. So either the null is true or it's false. So we either live in the world that's represented by row 1, or we live in the world that's represented by row 2. Those are mutually exclusive, different worlds. Okay? Think about the columns sort of differently. The columns are what we do as the experimenter or as the researcher. We have to make a decision based on that p-value, based on our data. We are either going to decide to retain the null or reject the null. We have to make this binary decision. Again, that's one of the things that people don't like about this is that sort of strict decision rule. You have to reject or retain, that's it. But that's how the game works. So you retain or you reject. So you're going to wind up in one of these four outcomes. So if you retain when the null is true, great, you made the correct decision. Likewise, if you reject when the null is false, great, you made the correct decision. But there's always the possibility of an error. And there are two types of errors. The first is a type 1 error or false alarm. That's where you've rejected the null hypothesis when in fact there wasn't a relationship there. That's why it's called a false alarm. That's like doing a vaccination study and claiming that the vaccine works when in fact it really doesn't. Sometimes that happens. Sometimes there are fluke results. Or you could do test a new drug to see if it's effective in treating, say, HIV. And you might get an initial result that looks good and say, hey, this drug works. But then as you do more research, get more representative samples, better assessments, you might find out, hey, it doesn't work. So that would be a type 1 error. There's also the possibility of a type 2 error, and that's called a miss. So there's really an effect out there, and you just missed it for whatever reason. Maybe you had poor assessment, maybe you didn't have enough subjects, you didn't have a random representative sample. For whatever reason, you may have missed it. So there's always the possibility of a type 1 error or a type 2 error, and we have to live with that. Because research is messy a lot of the time, and we're doing this inference process where we're getting a sample from a population. So we're engaged in these estimation procedures. There's a lot of probabilistic outcomes. So we just have to be comfortable with the fact that we might make mistakes in individual studies. But that's okay because we do lots of studies. Right? You don't do one experiment and then say, hey, this vaccine works or this drug works. It takes multiple studies, replications. So if you're uneasy with this and the fact that we're going to make errors sometimes, remember that we're going to do lots of experiments or lots of studies, or if you're a consumer of statistics and research, look for replications. Never base a conclusion on one individual study because they're prone to these errors. So to be clear, and this is one of the most important things I tell my undergraduate students to walk away from my course with, is knowing that the p-value that you see in the news or in a research paper or in your R output, what does it mean really? It's the probability of obtaining the data you obtained given the assumption that the null hypothesis is true. Okay? It is not the flip of that, which is what a lot of students do. And actually, even PhDs, not my colleagues here at Princeton, they wouldn't make that mistake. But I've seen people do it. They often get this outcome and then they just mistakenly flip it around and say, oh, well, then it's the probability of this hypothesis given the data. So the probability that the null is true is very low. That's not true. You can't make that reverse inference. So again, this top line here is one of the most important things I want you to take away from this course. Even if you only watch this one lecture, please know that. When someone says that something's statistically significant, p less than 0.05, what it means is it's the probability of obtaining those data given the assumption that there was no effect or no relationship in the study or experiment. So far in this course, we've only done two procedures that we can apply NHST to. So we've done correlation and regression. We're going to apply NHST to lots and lots of statistical procedures going forward. So far, we've only done two. So when we do correlation analyses, we can say, well, is the correlation between these two variables, is it significantly different from zero? Again, that's that phrase statistically significant. That's where it comes from. And we could ask in a regression analysis, is the slope of the regression line for x relating to y significantly different from zero? And if so, then we would conclude and we would write up in our paper, and perhaps the newspaper would pick it up. They would say, well, researchers found a significant correlation between, a statistically significant correlation between working memory and intelligence. Right? That's something that we found before. It's a significant correlation when you do the NHST procedure and a correlational study. So far, that's all we've been able to do with NHST. So in the regression example, I want to point this out to you because you'll see this in the lab where you start to do multiple regression. You'll see lots of t-tests and lots of p-values. So it's important that you start to understand what these things are because you're going to be seeing this in a lot of your R output in lab and as you do the next assignment. So the way to get to this p-value that we've been talking about is to first calculate a t-value. And I'm going to cover all of this in more detail in the lecture on the central limit theorem. We'll get into the nitty-gritty of these t-values and p-values and their relationship. But for now, I just want to show this to you because you're going to see it in your R output. So the t-value is just the regression coefficient relative to the standard error of the regression coefficient. And it's a ratio. And most NHSTs are essentially just ratios. And they're basically what did you observe relative to what do you expect just due to chance, right? That was standard error. Standard error was how much sampling error are we going to get just due to chance? The regression coefficient is what we actually observed. So if what we actually observed is a lot stronger than what we expect just due to chance, then we'll get a high t-value, and that's going to result in a low p-value and a statistically significant result. In contrast, if my regression coefficient is the same as what I would expect just due to chance error, so if b is equal to SE, then we get a t of 1, that's not going to give me a low p-value. That's not going to result in a statistically significant result. We would have to retain the null hypothesis in that case. And you'll see this in the R output, and we're going to cover the underlying math of this in much more detail when we cover multiple regression. So to summarize this segment, NHST is simply a procedure for hypothesis testing, and it's just one procedure. There are other ways to engage in hypothesis testing, which I'll talk about in the next segment. And I said I like to just think of it as a game. We're playing a game, NHST, makes it a little less controversial if I think of it as a game. It requires this binary decision, so you either reject the null hypothesis or you retain it. And what that means is there's always going to be 4 possible outcomes. 2 are great, correct retention, correct rejection, and 2 are errors. The type 1 error, false alarm, type 2 error, a miss.